Hi, welcome to my talk. Thanks for the attention. I'm Pim Venderbosch. I'm the software lead at QuiX Quantum. And I'm going to talk today about quantum computing using photonics. That's what QuiX Quantum is about. And our mission is to create a unique solution for scalable quantum computing, and we use light for that. And our saying is, photonics leads quantum, and QuiX Quantum leads photonics. And I'm going to try to convince you in this talk. I can be short about this slide because I assume that many of you know that there are a few industries where quantum computing can make the impossible possible by solving problems that we cannot solve with our current hardware, classical computers, and it's expected to be a big market in the future. So then, how do we fit into this, into the quantum computing market? Yeah, so we have a product portfolio that looks like this. We started out in 2019, and only a year later we have released our quantum photonic processors, and they are already sold to many universities and quantum computing companies, and they mainly enable researchers and quantum companies to do experiments much faster than they were used to using their tabletop photonic experiments. And we have integrated that into one device that is much more configurable. Later this year, we will put that photonic processor in combination with photon sources and photon detectors online available on a cloud. And if you have the photon source and detectors, you can already sort of experiment and see near-term applications in healthcare, finance, logistics, and this is very, very hopeful for the near term. But we're extremely focused on the long term, and in our opinion, that is moving towards universal quantum computers. The special purpose quantum computer may solve some problems, but with universal quantum computers, we really unlock all the capabilities of quantum computing. And I will say a bit more about it later, but 2027 is the point on the horizon where we want to have our first universal quantum computer. Many people think of quantum computing this way, where you see a big refrigerator with a lot of wires, and then the quantum chip all the way at the bottom. But for photonics, it looks a bit different. This, by the way, is the Google Sycamore setup, which showed the quantum advantage. A similar experiment has been done in photonics, and that looks like this, which is still a bit bulky, but it's very impressive work what they did there. They showed quantum advantage in a free space way. Our system is integrated. We use integrated waveguides to channel our photons, and then it looks much cleaner, and there's way less bulkiness, and that creates a much more scalable solution. And the system that you see here is the one that we're going to put out online in the cloud later this year. So then, in the core of our products, it's always about the quantum photonic processors. And there you basically map photons on qubits. So you use photons as your qubits. You use the photons' interference with each other to manipulate your states. And then in the end, your computation comes from doing measurements on those photons. Of course, we have technical challenges with the photonic approach, but we have a very good idea of how to solve them. I will go in a bit more detail of these four these 4 categories in the next few slides. So first of all, you need to reduce the errors. Luckily, photonics is not very prone to errors. We don't really pick up noise from the environment. There's almost no decoherence, and that's really a good aspect of photonics. But we do have another source of error, and that is losses, and they sort of come in the equation much like decoherence in other systems, and so that means that you need to keep the losses of all of your chips as low as possible so that you don't lose your photons. Luckily, we are really good at that. We are using silicon nitride in the triplex technology, and what you see here is the latest published losses that we have, which are very low if you compare them to other photonic devices, and we're also doing a great effort in improving them even more. Then a quantum computer can only be reaching the useful size if it's really scalable. So what we have the advantage with photonics is that it is integrated. We can use a lot of components from the telecom networks that are out there already today. So there's a lot of technology crossover that we can depend on, and that makes it quite nice for us. And to get this scalability in, we really depend on modularity. So you create components that are of high quality and that can create your entangled states in a very, very controlled manner. And then because we are using photonics, and that's basically the next point, we can create these modules together quite easily. So that we do, let me go skip over one, that we do with quantum photonic links, and that's basically an optical fiber from one module to the other module, and that way you can use that modularity to scale up quite easily, and then you just need to make very good modules. And the last technical challenge is cooling for quantum computing in general. We do need some cooling in photonics, but it's not as bad as for other technologies where you basically need to cool the entire thing. In essence, photonics works at room temperature. As I said, you don't really pick up environmental noise. So the 3 main components, 2 of them can actually live at room temperature. So these are sources, we can have them on chip, we can do on-chip manipulations, all at room temperature. Only for the detectors, we need to go down to cryogenic temperatures, but that's only 4 Kelvin, which is not as hard as millikelvins, for example. So our current status is that we have sold already more than 10 processors worldwide to researchers and quantum startups. We have we have gotten like in total 9 million euros of investment. But a very big achievement that we reached last year is that we sold the first universal quantum computer to a DLR, the German Aerospace Center, and that is actually what we are really working on right now. Going to the universal quantum computing and doing that over the next 4 years, moving to universality and then scaling up to many more qubits to go into the useful regime. I will skip over this for now. We have offices in the Netherlands and in Germany. We're starting up now in Germany as part of this German collaboration, and basically we're expanding fastly. So we're also, let me see. Yeah, so we're also at the Quantum Delta exhibition space that is over on the right side. So I'd like to meet anyone who's interested over there, or at the drinks at the end of the day. Thank you for your attention.